Third question A, define force. Force is nothing but rate of change of momentum. Basically, if a force applied in this direction, force is defined. Obviously, this is having a mass, this object will have mass m, right? Now, momentum is equal to mass into velocity. Obviously, we know from second law that if force is applied on an object in the same direction, velocity will be changing. Velocity will be increasing in this particular case. So, there will be change in momentum. Mass won't change, but velocity is changing. So, there is change in momentum with respect to time. So, force is defined as rate of change of momentum with respect to time. That's it. Or it basically gives us an idea how your momentum is changing in a particular direction with respect to time. Now, Newton's third law is very famous. It is every action has equal and opposite reaction. For example, if there is a book in a table, okay, so book is in contact with the table, so it will be applying a weight on the table, surface of the table, which force will travel through this legs of the table to the ground. Okay, to the ground. Now ground will exact equal force back into the table, and this table surface will apply exact same force back into the book. Okay, so here the weight is the action and this is normal force, it is called, which is exactly opposite to the weight applied here particularly. Okay, is equal and opposite. This normal force is reaction force, which is equal and opposite to the action force W. Its weight. Okay, every action has equal and opposite reaction. That's why the book doesn't break the table and go down. Okay. Because the forces are balanced here. Now, two spheres approach one another along the line joining their centers, illustrated in figure 3, as you can see. They are basically traveling opposite to each other through one single line. Okay. When they collide, the average force on the sphere A is Fa, the average force on sphere B is Fb. Okay, the force applied by B to sphere A is Fa, and force applied by sphere A to B is Fb. Okay. Now, state the relation between Fa and Fb. Now, applying Newton's third law here, if you consider this is action, this will be its reaction. Okay, that means I can write Fa is minus Fb. Their magnitudes are equal and it is in opposite direction. Okay, equal and opposite. That's it. I'll write this relation here. Fa is equal to minus Fb. Now the forces act for Ta on the sphere A, Tb for on the sphere B. See, when they collide with each other, okay, the contact time, basically the contact time are common for both, right? So I can write from this analysis, I can write Ta is equal to Tb because this contact time is mutual, right? So force acting on each other will be acting for mutual amount of time. Hence, TA is equal to TB. Now I have equation 1 and equation 2. They are saying that use your answer from 1 to show that the change in the momentum of sphere A is equal to the magnitude and is equal in magnitude. Basically, the momentum change in sphere A is equal in magnitude and opposite in the direction of the change in momentum in sphere B. Basically, momentum change in sphere A is equal and opposite to sphere B. Okay. Now, these are two equations. So I can write FA. I'll just multiply equation 1 with equation 2. So FA into TA is equal to F minus FB into TB. Now, you see, if you just look at it, see, F force is equal to change in momentum with respect to time. Now let us consider time interval is any time t. Okay, so del p is f into t, right? Hence this FATA that we are finding out, it is del PA, and this is basically minus del PB. They are equal and opposite, right? From this, I can write this is PA, del PA, and this I can write minus del PB, and there is a equal sign in between, so I can put equal, so I know that del PA is equal to minus del PP. So I can write change in momentum is mutual, which is equal to FATA, and they are opposite. How do I express it? By equation. Okay. Okay. For the spheres in B, the variation of time of the momentum for sphere A before and during and after the collision with sphere B is shown in the figure 3. Okay, 3.2. Now they're asking us to complete the graph. Okay, this is before collision. Okay, and collision is occurring till this point, and then after collision. Okay, before collision, after collision. Now, Pi, initial momentum of both the spheres will be, you see, it is 5.56, 6 newtons, positive 6 newton second for sphere A, and this is negative 4 newton second for sphere B. This is the initial momentum. Final momentum will be, you see, the sphere A now gains negative momentum. That means it is now moving in the opposite direction. That is what they are trying to say. And this is 3 Newton second, as you can see here, minus 3 Newton second, I'll write, plus PB obviously will be positive. Sphere, I mean, momentum of the sphere after the collision is PB. Now, I can use the momentum conservation PF. So 6 minus 4 is equal to minus 3 plus PB. From here, we get PB to be 5 Newton second, positive 5 Newton second. So 5 is here. Okay. Now, you see, the time taken in T1 is equal to T2, TB, right? T-way is equal to TB. So here also collision will take same amount of time. So from here to here, it remains constant. After that, from here onwards, it again remains constant, becomes 5. And in between, it is going through momentum change. So this is how the graph would look like. Okay.